the quiz that we have just given. It is ethylene. So I have to emphasize again that you have to know that what is the chemical that you are working with. For example, in this case, you have ethylene. So you must use the information for ethylene, not other chemical. And you have ethylene at 1 atm and it's cool. The temperature is lower from 170 degrees to 0 degrees Celsius. By direct heat transfer to the surrounding temperature, the temperature of the surrounding is 25 degrees Celsius. What is the loss work? And the unit that we would like to calculate is kilojoule per mole. So when you work on any problem, you must figure out what is the concentration and you have to use the information for that chemical. Next, you have to know what is the pressure. This is P1 and this is P2 and it's equal to what? The temperature is 170 degrees Celsius. This is T1, the initial temperature or the entering temperature 170 degrees Celsius. And the final temperature is 0 degrees Celsius. Okay, so the temperature of the surrounding is 25, so this is T sigma. So the first step of working on the solution is to write the process and label the variable you know. For example, in this one, P1 is 1 atm. P2 is also 1 atm. Then this temperature is 170 degrees Celsius, or in the Kelvin unit, it will be 443.15 Kelvin. And it will exit the process now at 0 degrees Celsius, or in the Kelvin unit, it is 273.15 Kelvin. So we were asked to calculate W loss, which is actually W dot loss over N dot. We know that this value is just the product of T sigma and Hg. So according to the problem statement, T sigma is 25 degrees Celsius or 273.15 Kelvin. So what left us to do is to calculate Hg. Okay, according to the entropy balance that we have studied in chapter 5, Hg is the Hg dot is equal to delta N dot S plus dNs by dt of the control volume, and then minus summation J equal to 1 and Q dot j over T sigma j. However, we will divide both sides of the equation by n dot, and we are interested in the steady state condition. So we obtain Hg become delta S and minus Q dot J. Since we only have one surrounding, so we only have J equal to 1. So it must be Q dot divided by T sigma. And our W loss will become plus T sigma delta S and minus Q dot. Okay, from your energy balance, you look at this system and you perform the energy balance, you will obtain the following equation. D by dt. This term will be zero anyway because it is steady state. Will be equal to minus delta m dot h plus u square over 2 plus gz plus q dot plus w dot s. There is no work, so this term will be zero. There is no kinetic energy change, there is no potential energy change, so you end up with q dot will be equal to delta n dot h. But you divide both sides by n dot and you obtain q dot will be equal to delta h. So in other words, the loss will just be equal to minus delta h. Okay, and plus T sigma delta S. Okay, I will do the calculation by two ways. The first one is I am going to use the NIST database. And the second one is I am going to use Appendix C. So that in this case, delta H will become integrate from T1 to T2 CPIG over R dt. And you use the information given in Appendix C. CPIG over R equal to A plus BT plus CT square plus DT to the minus 2, and you do the integration. And delta S will be equal to R integrate from T1 to T2 CPIG over R dt over T minus R natural log of P2 over P1. And then I substitute into the equation for W loss. In doing so, I will make this term become zero because P2 is equal to P1 and natural log of 1 is 0. So I will use Microsoft Excel for the purpose. And of course, I have to use my Google Chrome in order to access NIST database. I will do so by first go on to Microsoft Excel. Next, I will go on to NIST database, which if you do not know, you just search NIST fluid properties. And then, so we must select the chemical. The chemical now is ethylene, but according to IUPAC, we can call ethylene ethene. We keep the Celsius, we select the Celsius, we select the ATM, we select kilojoule per mole, and then we select isobaric because we know that the pressure is constant at 1 atm. Of course, we put in the pressure of 1 atm. We put in the temperature of 0 degree. We put in the temperature high of 170. And since we do not want any further information to interfere with us, so the increment is 170. And then press for data and look at the data in the HTML table. So what we have to do next is to put in the respective value of corresponding value of enthalpy and entropy into the appropriate cell. For example, T1 is 1, T1 is 170, and at this state, the enthalpy is 25.778 and the entropy is 121.2T divided by 1000. And when the temperature is 0 degrees Celsius, the enthalpy is 17.45 and the entropy is 97.846 e to the minus 3 means divided by 1000. Okay, this is for heating. Okay, of course, it's correct. So then we determine W loss from the information I just discussed about minus delta H and plus T sigma, which is 298.15 multiplied by delta S, which is the difference between S2 and S1. And the unit will be kilojoule per mole. This is the approach that I prefer, use NIST database. The second approach is for me to use the table C1 in order to calculate the enthalpy and to calculate the entropy change. So what we should do here is we must change the temperature to be in Kelvin. So 273.15 multiplied by 170, it becomes 443.15 and T2 become 273.15. And according to table C1, A is equal to according to table C1, A is equal to 1.424. B is equal to 14.394 e to the minus 3 and C is equal to minus 4.392 e to the minus 6 Okay, let me explain something to you now. If I calculate CPIG over R at T1, I will be able to calculate it from this value of A plus this value of B multiplied by T1 and then plus this value of C multiplied by T1 squared. So CPIGY is 6.94 and CPIG over R at the temperature T2 will become the following: A plus B times T2 plus C times T2 square. Sorry, I think okay, time. Okay, so as you can see, the difference between the CPIG over R at these two temperatures are a lot. We cannot assume CPIG over R as the constant, and similarly, we cannot assume CPIG over R over T as a constant, and we do have to do the integration according to the procedure that we have learned in our calculus 1, calculus 2, and calculus 3. So we can calculate our delta H by using the formula we have discussed in the class. So 8.T14 multiplied by A multiplied by the difference between T2 and T1 and then plus B divided by 2 multiplied by T2 square minus T1 square and plus C over 3 multiplied by T2 cubic minus T1 cubic. This is our delta H with the unit of Joule per mole. And similarly, we can calculate delta S from the integration of CPIG over R dt over T from T1 to T2 minus R natural log P2 over P1, but P2 is equal to 1, P1 is equal to 1, so natural log of 1 becomes 0, and we have only the first term. So delta S will become 8.314 multiplied by A times natural log of T2 over T1 plus B multiplied by the difference between T2 and T1 plus C over 2 multiplied by T2 square minus T1 square. And that's it. The unit for delta S is Joule per mole. As a result, our W loss will become minus delta H plus T sigma, which is 298.15 multiplied by delta S. Of course, this unit is Joule per mole. So if I would like to change the unit to kilojoule per mole, I have to divide this one by 1000. So it is Joule per mole. Okay, these two approaches are acceptable, but I have to inform you that this one is always more accurate. Again, you can either work with this method or you can either work with this method. Those two methods are okay for this class, but I would like to emphasize again that actually the one that use NIST fluid property database is more accurate. Therefore, I would like to end the solution of the quiz now. If you have some question, please feel free to contact me. Bye bye.